Heads or tails? Welcome to the quantum world. Imagine flipping a coin. It spins in the air, a blur of possibilities. Is it heads or tails? Until it lands, we say it's both. This is the essence of superposition. In our everyday world, things are definite. A light is on or it's off. But in the quantum realm, the rules are different. Particles like electrons don't have to choose just one state. They exist in a mixture of possibilities, a kind of blurry, undefined state. Think of a spinning coin frozen in midair. It's not heads or tails, it's heads and tails, all at once. This isn't just a quirk of tiny particles. Superposition is fundamental to how the universe operates at its most basic level. It's a concept that challenges our intuition, forcing us to rethink what we thought we knew about reality itself. Superposition, beyond the coin toss. Imagine flipping a coin. It spins in the air, and for a brief moment, it seems to be in a state of uncertainty. Will it land on heads or tails? This simple act of flipping a coin is a classic example of probability in our everyday lives. But what if we told you that there's a realm where this uncertainty is taken to an entirely new level? Let's move from our coin to something even smaller, an electron. In the quantum world, the behavior of particles like electrons is governed by principles that are far more complex and intriguing than a mere coin toss. In the quantum world, an electron doesn't have a fixed location like a planet orbiting the sun. Instead of following a predictable path, an electron exists in a state of uncertainty. It doesn't have a single defined position. Rather, it occupies a range of possible locations, all at once. Instead, it exists as a wave of probabilities, spread out like ripples on a pond. Imagine dropping a pebble into a still pond. The ripples spread out in all directions, representing the various places where the electron might be found. This wave-like nature of the electron is a fundamental concept in quantum mechanics. This wave, called a wave function, describes the likelihood of finding the electron in any given place. The wave function is a mathematical description that provides the probabilities of an electron's position. Peaks in the wave function indicate higher probabilities, while troughs indicate lower probabilities. It's like a map of possibilities, with some areas more electron-dense than others. Think of it as a heat map, where the intensity of color represents the likelihood of finding the electron in that region. Some areas are hotspots, teeming with higher probabilities, while others are cooler, less likely zones. This is where superposition comes in. Superposition is a principle that allows the electron to exist in multiple states at once. It's as if the electron is in several places simultaneously, a concept that challenges our classical understanding of reality. The electron doesn't have to choose just one location on this map. It exists in all possible locations simultaneously, a mind-boggling concept that defies our everyday experience. This simultaneous existence in multiple states is what makes quantum mechanics so fascinating and perplexing. It exists in all possible locations simultaneously, a mind-boggling concept that defies our everyday experience. Imagine trying to pinpoint the location of a single electron, only to find that it could be in several places at once. This is the essence of superposition, a phenomenon that has profound implications for our understanding of the universe. It's only when we try to measure the electron's position that this superposition collapses. The act of measurement forces the electron to choose a single location, collapsing the wave function into a definite state. This collapse is a key aspect of quantum mechanics, highlighting the role of the observer in determining the outcome. The act of observation forces the electron to choose a single location, like our spinning coin finally landing on heads or tails. Just as the coin's uncertainty is resolved when it lands, the electron's position becomes definite upon measurement. This interplay between probability and certainty is at the heart of quantum mechanics, taking us far beyond the simple coin toss into a world of endless possibilities and profound mysteries. Schrödinger's cat, a feline paradox. To illustrate the strangeness of superposition, Erwin Schrödinger, one of the pioneers of quantum mechanics, devised a thought experiment. Schrödinger was a brilliant physicist who made significant contributions to the field of quantum mechanics. His thought experiment, known as Schrödinger's cat, was designed to challenge our understanding of quantum theory and its implications. Imagine a cat sealed inside a box with a device that has a 50-50 chance of releasing a deadly poison. This device is connected to a radioactive atom, which has an equal probability of decaying or not decaying within a given time frame. If the atom decays, the poison is released, and the cat dies. If the atom does not decay, the poison is not released, and the cat remains alive. Until we open the box, we don't know if the cat is alive or dead. The cat's fate is intertwined with the state of the radioactive atom, creating a scenario where the cat is in a superposition of both life and death. This uncertainty is at the heart of the paradox. According to quantum mechanics, the cat exists in a superposition of states, both alive and dead at the same time. This concept is difficult to grasp because it defies our everyday experiences and intuition. In the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. Of course, this seems absurd. The idea that a cat can be both alive and dead at the same time challenges our understanding of reality. It forces us to reconsider the nature of existence and the limitations of our perception. Our intuition tells us the cat can't be both alive and dead. We are accustomed to a world where objects have definite states, and the concept of superposition seems alien and counterintuitive. This is why Schrödinger's thought experiment is so powerful. It highlights the disconnect between the quantum world and our everyday experiences. And indeed, once we open the box, we'll find the cat in one state or the other. The act of observation collapses the superposition, forcing the cat into a single, definite state. This is known as wave function collapse, a fundamental concept in quantum mechanics. Schrödinger's cat wasn't meant to be taken literally. It was a thought experiment designed to illustrate the peculiarities of quantum mechanics and provoke discussion about the nature of reality. Schrödinger himself was skeptical of the implications of his own experiment, and he used it to highlight the paradoxes inherent in quantum theory. It's a powerful illustration of how the rules of the quantum world clash with our everyday experience. The quantum world operates under a different set of principles, where particles can exist in multiple states and outcomes are determined by probabilities rather than certainties. It highlights the bizarre nature of superposition and the profound implications it has for our understanding of reality. The thought experiment of Schrödinger's cat continues to be a topic of fascination and debate, reminding us that the universe is far more mysterious and complex than we can imagine. It challenges us to expand our minds and explore the boundaries of human knowledge. Collapsing the wave. Function observation changes everything. In the mysterious world of quantum mechanics, the act of observation is not just a passive act. It fundamentally alters the very nature of the system being observed. This phenomenon is one of the most intriguing aspects of quantum theory and has profound implications for our understanding of reality. The act of observing a quantum system plays a crucial role in superposition. Superposition is the principle that a quantum system can exist in multiple states at once. However, this delicate balance is disrupted the moment we attempt to measure it. The mere act of observation forces the system to choose a single state, collapsing the superposition into one definite outcome. When we measure a particle's position, momentum, or any other property, we force it to choose a single state. This measurement process is not just a passive recording of information. It actively influences the particle, compelling it to adopt a specific state out of the many possibilities it previously held. This is a cornerstone of quantum mechanics and is known as the measurement problem. This is what's known as wave function collapse. The wave function, which describes the probabilities of a particle's various states, collapses into a single state upon measurement. This collapse is instantaneous and irreversible, marking a clear transition from the quantum realm of probabilities to the classical world of definite outcomes. Imagine shining a light on our spinning coin, suddenly able to see which side faces up. Before the light is shown, the coin is in a state of superposition, spinning with both heads and tails as possibilities. The moment we observe it, the coin decides on one outcome, much like a quantum particle does when measured. That's like making a measurement in the quantum world. The act of measurement disrupts the superposition, forcing the system to settle into one of the possible states. This disruption is a fundamental aspect of quantum mechanics and highlights the active role of the observer in the quantum realm. The act of observation disrupts the superposition, collapsing the wave function into a single, definite state. This collapse is not just a theoretical concept, but has been experimentally observed in numerous quantum experiments. It underscores the intimate connection between the observer and the observed, a relationship that challenges our classical notions of reality. This raises a profound question. Does observation actually create reality? If the act of observing a quantum system determines its state, then to what extent are we, as observers, shaping the reality we perceive? This question has sparked intense debate among physicists and philosophers alike, leading to various interpretations of quantum mechanics. It's a question philosophers and physicists continue to grapple with. Some interpretations suggest that reality is fundamentally probabilistic until observed, while others propose that all possible outcomes exist simultaneously in a multiverse. The debate is far from settled, and each perspective offers unique insights into the nature of reality. Some argue that consciousness itself plays a role in collapsing the wave function, suggesting that the mind is not just a passive observer, but an active participant in the creation of reality. This idea, known as the consciousness causes collapse hypothesis, posits that the observer's mind is integral to the process of wave function collapse, while others believe it's a more fundamental aspect of the universe. Regardless of the interpretation, the observer effect remains a central concept in quantum mechanics. It highlights the profound and often counterintuitive nature of the quantum world, where the act of observation is inextricably linked to the reality being observed. The observer effect highlights the intimate connection between the observer and the observed in the quantum realm. This connection suggests that our role as observers is far more significant than previously thought. We are not merely passive recipients of information, but active participants in the unfolding of reality. It suggests that we are not passive observers of the universe, but active participants in shaping reality. This realization has profound implications for our understanding of the universe and our place within it. It challenges us to rethink the nature of reality and the role of consciousness in the quantum world. But active participants in shaping reality. As we continue to explore the mysteries of the quantum world, the observer effect serves as a reminder of the deep and intricate connection between the observer and the observed. It invites us to consider the possibility that our very act of observation is a fundamental part of the fabric of reality itself.